Sounds like Kate's
Okay.
doing something similar.
It's working. All right. I want to go over maybe one or maybe two examples of doing volumes where you have a known base region and then all the cross sections are like a known shape. And then we're gonna move on to solids of revolution, where you take a region and you spin it around one of the axes. And you kind of carve out like a vase.
A vase.
Pronouncing it vase is just a hilarious meme to me. That's how you know you're upper crust if you say it vase.
Upper crust. Never heard that.
Really?
Nope.
Like upper class.
Well, I get the reference, but
Mr. Hall, did you hear that Burger King tweeted that women belong in the kitchen?
Oh yeah, I saw that.
no.
Did you open the comments though?
Yeah.
They're doing it for
Today?
they're trying to make it like a pro
Yeah,
Yeah.
it's like
women's
there's
rights
not very many
argument, but
women in the
How does one make that a woman's right argument?
They tweeted it like
It's because like only 20% of the
Only 20% of women like have down in the kitchen, saying like we should have more jobs.
Ah.
But they like only tweeted.
Yeah, they
We're-
That wasn't good. On
So the social
Women's Day.
media
That is bad.
And then they like replied to it and they were like, what are they hired to do this?
How do you even do that on accident?
KFC
We're gonna look at number two.
Two, thank you.
the correct time to delete this food when you made it.
I'll watch your video on Friday.
Did you give any gifted subs?
Do you want me to start subbing?
Any gifted subs? And mints. I live for mints.
I was kind of lost when you only posted 3 videos like last week, and I need Kate's help because I could only figure out
Oh, you
like
missed some work days.
I know, but I couldn't figure out how to do how.
Okay, so this is the curve y equals 2 over x. Okay, we're all fine with that, right?
Yes.
All right. So then it says also x equals 1. So I'm going to try to draw this roughly to scale, but not going to be too super bent out of shape if it's not like ultra proportional, but you get the idea, right? And then y equals 0, of course, is just the x-axis. Okay, so do we also the region?
Squarish.
That's fine. That's fine. Okay, so so what would this look like if all of the cross sections were squares perpendicular to the x-axis? Meaning, if you took your knife and held the knife perpendicular to the x-axis and sliced it, and then you turned the loaf sideways, what shape would you see? It's a square. Very good. So let's examine one of those squares. Let's say I slice right around here. It would slice. Let's remove that little slice of bread. Because I mean, here's the region, but I'm just going to take one little slice out of that. So let's pull that slice out, and it looks like this. How thick is that slice of bread?
Dx.
X. Dx. And then the dimensions, how tall is it?
2 over x.
Yeah, it's the y value of this curve, so 2 over x. And then, of course, it's critical to, that you have the shape given, because if they don't specify what kind of cross-section it is, you can't really do much, but it says it's a square, so that's 2 over x. All right, so we feel okay so far.
Yeah.
So then we ask, what's the volume of that slice, that tile, or slice of bread, whatever you want to think about it as? What's the volume of it? Well, this times this would be 4 over x squared times dx. By the way, if you want some food for thought here, we're not going to really, let me just mention this. This is not super critical to doing this, but it's interesting. And this is a bigly thing for if you go on to higher, if you keep studying calculus like university. You could say something like this. You could say that What I just described here is actually a tiny little element of volume. A dv, meaning it's like dx is a small little bit of x, and then dv is a small little bit of volume. So technically what you're doing is integrating both sides, and then of course the integral of dv is just v. So just some food for thought for that. So the total volume would be, what's our bounds of integration? 1 to 4. X values, of course. X values. Okay. Calculation time. So this is 4 times x to the -1. So that's going to become, -2. Got a little ahead of myself there, right? So that's going to become but yeah, basically -4 over x. Everyone understand that?
Why?
Because that's
No,
yeah,
I
yeah.
was just wondering why you put it back up top. guess.
I was just, this is my margin. This is me
Yeah.
just, if you can go straight from this to this, that's good. Because we don't want to write like multiple steps of all the integrals where we're showing every little tiny step
Oh,
ideally.
okay.
So I was just saying in my margin, I might show something like this. Like, yeah, that's how it works. So then we go from 1 to 4. Okay, time to plug in. Let's plug in the 4. -1 minus. Plug in the 1. 4. Here's the hardest part. Just kidding. That's kind of amazing. Just an integer. 3. That's neato. Isn't that remarkable?
Fantastic.
Okay. By the way, number 4, I think I'm going to save that one for you, but number 4 is this. It's a circular base. There's the base, and then all the cross sections are squares. So if you slice that circle in the middle, right, you get a pretty big square. And the square is the diameter of the circle, right? That's the side line. But if you slice the circle towards the side, you get a smaller square. So I think 4 is a good one. I feel pretty confident that you should have no trouble. The hint is you solve for y, right? So your curve there is going to be y equals the square root of 1 minus x squared, which you might go, well, that's hard to integrate. But you're going to be squaring that because all the little pieces are squares. It's actually very easy. It turns out to be a pretty easy integral. All right, what I want to look at with y'all would be, let's look at 5. So read that. Maybe draw one of the slices. So it describes a region. You might also notice that sometimes they do this. They'll name the region. They'll give the region a name like S, and we'll just refer to S later. Just kind of shortens things up. All right, what does S look like? There's y equals root x. There's x equals 9. And here's the x-axis. So the first question says, what if all those cross sections were equilateral triangles perpendicular to the x-axis? This is actually one I showed you in class, I think, on Friday. Remember the green? Mm-hmm. Yeah. Each triangle went boop, 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 boop. So anyway, like a triangle down here would be pretty small triangle poking out of the board. It's kind of like a mountain ridge a little bit. Because these are such small triangles down here when you slice them. But over here, they're pretty tall triangles. Making sense? Mm-hmm. And hopefully also either you recall or you can refer to this note. area, so if you have an equilateral triangle that's L by L by L, some side length, the area of that triangle is root 3 over 4 times L squared. That's right. Did I recall that correctly? It was part E from the front, the first page. Okay, so let's examine one of these triangles. Let's look right here. Slice it. And then extract. Looks good enough, I think. What's the side length of my equilateral triangle? Square root of x. Good. So then what's the volume then of this? Oh, I forgot to ask the most important question. Dx is the thickness of the, kind of like when you get a peanut butter and jelly and they cut the crust off and they slice it diagonally. Isn't that beautiful? Man, it's a nice sandwich. It's put it in the panini maker. I don't know.
You put a PB&J in a panini maker?
Dylan, it would probably be a 45, 45, 90, but just let me have this. Anyway.
I'm still caught on you putting in a panini.
Yeah, you ever put a PB&J in a panini maker?
No.
It's pretty savage.
Yeah. Have to try one these days.
Stop.
What?
Are you on a list somewhere for that? You're a criminal.
Yeah, you are.
You are.
Dude, that is a good sandwich.
I don't know. I think it sounds good.
I agree. That is a problem, Mr. Hall.
You guys are nuts. That's good. Okay.
You make us all PB&Js from panini. I'll try it.
Well, yeah, I mean, I'm down.
So let's look at this. So anyway, what's the volume? The volume is this area, which we know we have a nice little tidy formula for calculating the area. So the area of this would be root 3 over 4 times the side length, which is just root x squared, right?
That's handy.
Times dx. Are we sure we understand that? That describes the volume of this little paninied peanut butter and jelly sandwich. Yes, Laura. Why is this?
No, the root x.
Because root x is the length, is the side length of the triangle. So we sure we understand?
Yes.
Mhm.
So what I'm going to do then is integrate that small bit of volume from, what are my bounds?
0 to 9.
0 to 9. Obviously, you want to make your life easy. I would probably just put that, well, it's kind of up to you what you want to do with it. I think it's easier just to take it outside of the integral. Oh, wait a second. There's something you're going to find a lot in these types of problems is because you're very often squaring the function involved, you end up going from like something that's very difficult, if not impossible to integrate, to something that's really easy to integrate. There's actually a famous result we're going to cover later. There's a famous shape that has it's a infinite surface area but finite volume. It's kind of weird. It's a horn. Imagine a horn. Infinite surface area. So if you wanted to paint it, it would be impossible because not enough paint exists. But you could fill it with water. It's kind of a weird shape. Anyway. You guys not surprising?
My head hurts.
It's kind of paradoxical. It's really fascinating because you can prove it using fairly simple math, basic elementary calculus. You ever heard of the Tarsky Paradox? You ever heard about that one?
The name is familiar.
They proved mathematically that, mathematically speaking, you can take a sphere and break it up into pieces and then rearrange those pieces into two identical spheres.
Yeah.
Maybe it was balls, I can't remember. It might have been balls, not spheres. But
What's the difference between a ball and a sphere?
a ball is three-dimensional, so it's solid.
Oh, I thought a sphere was three-dimensional.
Well, a sphere is the surface of a ball. So a sphere is a two-dimensional surface.
I've been lied to.
Well, it's like a circle versus a disc. So a circle is this. It's the set of points that's all these points. Whereas a disc, if I want to make a disc, I would make this. That's all the points that are. It includes all the points that are inside the disc. So, to make a sphere, you just go like this. Now it's a sphere. Oh, I'm sorry, it's a ball. Because
That's a ball.
Yeah, so a sphere would be an equal sign. Every point is exactly some number of units away from the center, and then a ball is all the points that are within that distance.
Okay.
Okay, anyway, sorry. Gabriel's horn was the name of the horn that I was talking about. First, in order to understand that one, you have to understand how to integrate the 1 over x function. The integral of 1 over x is the natural function. So we haven't covered that. Where were we? Sorry, where were we? Oh, the answer. Well, this is pretty easy, right? Facts and logic. So yeah, this is going to be half of x squared from 0 to 9. So you get 81 halves in the parentheses, right? And so 81 is not divisible by 4 or 2. So the answer would be 81 root 3 over 4. It's kind of a
That's a
not the
weird
nicest number, but it's kind of neat.
Why is it over 4?
area thingy.
Oh no, isn't it? That's
Yeah,
8. You're right.
8.
Sorry, it's 8.
Yeah.
Thank you. Right near that.
We were just
Testing you, obviously.
Yeah. I got
Just Lamal got it, you know.
Indeed.
You feel okay about that? All right, now let's compare that to. Well, I'm going to say B for you. B's the same thing. It's just imagine they're little Humpty Dumptys now. I was silly. I actually misread my own question. I wanted to do one where they're where one of them is. Okay, there's a couple options here. I wanted to do one where we're slicing it horizontally. Then I realized B is actually talking about
Calm out.
X axis again. But we can do 6 is a good one.
6?
Yeah, 6 is, or we can do a more complicated one, and then 6 you can come back to, and that'd be probably a pretty easy one to do.
Well, is that one
Let's do 7.
horizontal?
No, 7's a little bit more challenging, so,
Okay.
yeah, 7's a little bit more challenging, so you should be able to go back and 6 should be like an easy peasy, I think. Good practice for you. Awooga, exactly. Awooga.
Oh,
Awooga.
yes.
Who said that? Jason or
Jason.
Jason.
I said it while I was yawning.
Awooga. Indeed. Awooga indeed. All right. So 7. Look, behold. There's y equals 1/2 x. Here's the other guy. Y equals root x. Okay, so we're going to make this region is called H, and let's first do these cross sections that are perpendicular to the x-axis. Now, you guys, I'm sure, will be happy to see that you do not have to evaluate the integrals.
I'll go.
By the way, please include, maybe I should have been more explicit about this earlier, but the picture for these, I mean, it's definitely, it's an important part of the showing your reasoning. So make sure you include a diagram. So the slice. Oh, it's for you, Trey. Trey's reading Dune. Have you finished it yet, Trey?
Not yet.
It's like 3/4 of the way through.
The slice.
This.
Chloe's tone got me. Haven't you finished it yet?
Okay. Thickness, dx. And now these two side lengths are the same because they are squares. What's this? How far is that though? What's the height of that little square there? Square root of x minus half of x. Do we understand that?
Give me a sec. Yes.
It's this, so it's this y value minus this y value.
Yeah.
What's this guy's y value? Well, the y value is root x, of course, and then what's this guy's y value? His y value is half of x. Okay? So my volume then is the integral. What are my bounds? 0 to wherever they cross, which Trey says 4. It seems pretty on the ball. I'll trust him.
Yeah, I'd trust Trey.
Plug in 4, you get 2. Plug in 4, you get 2. Let's maybe mark that down while we're at it. Apparently plugging 4 in for x gets you 2 for y on both curves.
Apparently.
Apparently, they came directly across the Caribbean from Venezuela. Does George know where that's from? Maybe George? I don't know. Wu-Tang Killer Beats. Classic. Okay, so therefore then the volume is side length squared, right? We all understand why it's squared? Yeah. And multiplied by the thickness dx. Are we okay with that? Yes.
So, in like the other problems, you use like the x values like for their bounds. Does it matter if you use x or y values? Like, is that
Matters bigly.
so? Why do
this-
we use like y values in this one instead of x?
We already, well,
Oh, never mind. Just kidding. Never mind. I thought like 4 was the y. So never mind.
it's a good point to bring up though. I mean, technically this is a y value and this is a y value, but those are expressed in terms of x, so. And for part B, what we're going to do is we're going to change our perspective and we're going to make all the slices horizontal, which means the thickness is going to be dy.
So it means you put the y values.
Yeah, so our integral is going to be all y's. But then when we actually go to look at the width of that slice, they're going to be basically a difference of 2 x values if you think about it.
Oh.
So let's do the same problem again. Ready, spaghetti?
Let's see. That
Ready, spaghetti. The answer's right there.
made that a lot simpler for me.
We all understand what it means to say you don't need to evaluate, right?
Well, yes. But
Don't have to tell me twice.
All right. Oh no. Oh, okay. Same curves, same intersection points. Everything's the same. Okay, but this time you got to be like, well, as this thing, there's a bunch of differences. One, as we move and examine each slice, we're only going this time from 0 to 2. That's the first change. Let's examine one of these slices. So, like we mentioned a second ago, the thickness of the slice is dy, right?
mm-hmm.
And then the width. So what you're going to find is when you go to look for that width, that's going to necessitate being like, well, I guess the width of this is this guy's x value minus this guy's x value, right? Well, how do I write his x value in terms of y? You got to rearrange his equation, right? It should say x equals 2y. Do we understand that?
Mm-hmm.
Okay. And this guy should be x equals y squared. You feel okay about that too?
Yep.
Okay. So then this distance, this horizontal distance here would be 2y minus y squared. Isn't that nice?
Mm-hmm.
I'm so smart.
No one's mentioned it yet, so I guess I'll mention it. Does it matter if you go, what if you had swapped them and said y squared minus 2y? That'd be catastrophic.
Would that matter?
Why would it matter? It's not, you're right that it doesn't matter. You could
Oh,
actually
sweet.
swap them. Well, we're about to be squaring it, right? If we somehow had flopped them and it was a negative number at some point, well, it's getting squared anyway, so it would be fine.
So it
You can
only
test it out
works
yourself if you want at Desmos. So anyway, what we're gonna end up writing, so for example, you could have swapped those two terms. You could have wrote 1/2 x minus root x and evaluated numerically, and it's gonna be the same. So, does that make sense?
Yeah.
Does that only work with the square bits?
Just generally, if you're doing an integral and you have an item, an expression being squared, then you know that expression evaluated at any value must be positive, and thus it can't really matter if the tasty nougat inside was negative or positive because it's getting turned positive by the squaring. So okay, my bounds are between. My bounds 0 and 2 this time, so we're moving vertically, and the size of that disc, that tile or slice of bread is 2y minus y squared. That's the side length. So you got to square it for the area of the square and then multiply it by dy to get the volume of the tile. And there we go. We're done. That's it. Isn't that nice?
Yes.
Okay. I want to have a work day tomorrow, so I'm going to cover some more stuff. One more thingy. It's the same thing pretty much. It's not a big leap.
Which one?
We're gonna look. I think we got time to do 11 and 12.
Ghost.
Oh, that's a lot of that.
Solid.
What? They say it's going away around like 1.
No, I'm so sad.
Not good. Not good. Mr. Teletubby, how could you?
I was enjoying the sun in my classrooms. It was so warm. I always have the sunniest seats.
They should turn that back wall into a window.
They should. They should.
Okay, so this
The ceiling should
says,
be
11
entirely
says,
skylights.
you gotta read these real carefully.
Careful, like.
Careful like. So the region is y equals 4 minus x squared. The region bounded by 4 minus x squared and the x-axis. So can we all visualize that? You'll see it in your brain. And then here's the x-axis. So we're going to revolve that around the x-axis. So first of all, here's the region. You feel okay about that?
Mm-hmm.
And so now you got to engage the brain here. Imagine the three-dimensional space that this is living in. You might be going, well, isn't it a two-dimensional space? Doesn't it live on an XY plane? Well, we're about to revolve it around the x-axis. So it's going to carve out. Imagine this space being full of jello, like a perfectly pliable jello. It's gonna carve out like a cavity in the jello. So we're talking about what's the volume of that cavity. So just to what did he say?
Spoon.
Yeah, like if you swept a spoon through some area. So what shape is that?
It's like a tire shaped circle.
Yeah, some kind of wheel shape, kind of like a disc.
Skateboard wheel.
Maybe like a
No, like a rollerblade.
like a pill, maybe.
A pill?
Not the kind of pill that looks.
Circular?
Yeah, one of those more like rounder. Not the capsule. Not a capsule.
Yeah.
Yeah, kind of like a pancake, right? Like a thick pancake. That's a good example. So we understand. Can we all picture it in our heads?
Yeah.
You sounded like
So-
the rabbit when you said
The $1 million question of the day is: what is the fundamental shape involved in constructing this pancake? Not quite, because we're gonna do what we did before. We're gonna break this up into a whole bunch of little tiny slices. What is each slice gonna be if it's a revolution?
On the oval. The ellipse.
Who said circle? Very good, circle. We understand that.
What kind of ears do you have?
So imagine a little slice here, right? So here's a little slice.
Uh-huh.
Now imagine that slice carving out around the x-axis. It's going to form a disc, right? A circular disc. So let's visualize that disc. To draw a disc, you just draw like an elongated
That's not happening.
oval, and then you.
I can't make the S. This is. Oh, look at this.
Did you pass industrial tech?
Yeah, yes, actually.
You can it's not the best, but you could just draw this, and then as long as you understand that when you're drawing this, it's a circular disc.
It's a circle directly from the side.
How thick is the disc? dx. What's another prominent feature of the disc that we care about?
Radius?
The radius. So we want to know the radius of the disc. Now again, it's not 4. The radius is just the y value of the function, right? Do we understand that?
Mm-hmm.
People are often tempted, you probably imagine this mistake, right? The mistake would be, oh, I think it's half of 4 minus x squared. There are scenarios where that might be the case, but you have to imagine this disk here. I'm going to try to draw it carving out its place in the world. You see it now? There's that disk forming its contribution to the overall volume, right? And so the radius of that disk is indeed the y value of the curve. Okay? So I prefer this drawing. There we go. So hopefully that makes sense. If it doesn't make sense, that's normal, that's natural. You have to go into the thinky winky tank and understand what's going on here. So what's the volume of this little disk here? Well, the volume of that disk is pi r squared.
Well, we're trying to explain.
And then times the thickness of dx. Do you understand how this says pi r squared
Yes.
times the thickness? Now what's our bounds of integration?
-2 to 2.
-2 to 2. Or, because of symmetry, you could go from 0 to 2 and then double. That's certainly an option. Okay. And we're going to,
I missed it.
huh?
1 second. Okay. You're fine now.
And we all know how to calculate that, hopefully. So you have to expand it.
Do we have to solve these?
This one, yeah, says find the volume. It'll be okay, Lillian, don't worry. It goes on. Okay. So,
Oh, I don't think all of us do know how to solve that. Can you help us do that?
yes, we do.
Okay.
Okay, here you go, Caleb. It's for you, bro. You ready? All right. Let's take the pi out. He's a pest. Pi is a pest. Okay? And while we're at it, let's do what I just mentioned. Instead of going from -2 to 2, let's go from 0 to 2 and double it. Is that okay with everyone?
2 pi?
Okay, so I'm actually gonna call it 2 pi now and change my bounds to go from 0 to 2. We sure everyone's okay with that?
Mm-hmm.
Now, this guy is not, there's no u prime to deal with, so I have no choice but to expand this. So let's expand the binomial. 16 minus 8x squared plus the 4th. Yes?
Mhm.
Cool. Okay. So keep that 2 pi out there. Okay, let's integrate. Integral of 16. 16x. Integral of 8x squared would be 8/3 x cubed. Integral of x to the 4th would be and we put the bar inside. Now, isn't that nice? We went from 0 to 2 instead.
Yes.
Saves us, I mean, not a ton of work, but it certainly, we know when we plug in the 0, it's just going to make it 0, right?
Mm-hmm.
Yeah. That's how.
Do you explain?
Okay. Let's plug in. Okay, so we got to plug in the 2. You get 32. Minus. Uh-oh. Oh, no. No.
4/3.
You have to do 8 times 8. 64. Okay, everything's fine. Don't need to panic. Uh-oh.
What's 2 to the 5th?
32 fifths.
Ugh, that's a lot of nasty fractions. Gross.
Yeah.
Hey, would you like that?
Fine. Leave it like
Thank you.
that. That's AP standard anyway.
Oh, for sure.
If you're taking the AP exam and free response, you can just leave it like that.
But that's so
If this were an AP free response, this would, first of all, this would only be a portion of a question. This would be maybe like, it's probably 3 of the points. So the 9-point questions probably be part 1, 3-pointer. No, actually, this would probably be the third part. The first part would be what's the area of the region. That'd be like 3 points. If you miss in that, you're probably failing the test anyway.
Sounds like a blast.
Well, I'm just saying, like if you're taking a 9-point free response and you can't get the first couple points that are freebies, then you just weren't prepared. But anyway, the question would probably be like, find the area. Then maybe would ask you something like, maybe say we modify the function, how does that change the area, something along those lines. And then the last part would be like, say we revolve the region around
Bless
the
you.
x-axis, what would be the volume?
Bless you.
Anyway, but the final answer you can leave, you don't have to simplify. But this would be a point, that would be 1 point, and then this would be the second point, and then this would be the third point. That would be 3 points. If you're wondering.
Well, I'm wondering.
There were some good memes from, was it a couple years ago? This is a really famous thing in calculus, is like doing these volumes. And so on one test, they didn't put any volumes on it, which really surprised a lot of people. And then, but there was a question about a potato that had been heated up to some hot temperature. And it was a Newton's cooling question, but people were extremely triggered that they were like all geared up for this, like to solve the volume, and then they get potato. How hot
Will we
potato?
get to that by the time?
Yeah.
I think?
Hot potatoes?
Well, sure, yeah.
Yeah, we're gonna study hot potatoes.
See.
Potato.
I don't know why. Oh, I remember why I signed up for it. Because it was like half the price. Usually I would not take the last test. Did you sign up for it?
Not the game like that. I studied the game.
Did you sign up for AP? You just did Gov?
It should be professional.
Did you not even sign up for any of them? No. Sorry.
The last thing we gotta cover. Let's do one more example. This last example, this will illustrate the last idea you have to kind of understand about this stuff, which is very similar to how we take areas. Say there's a, like this idea. Got a curve. That's not very good. F. There's G. And I say like, oh, how much area is there between F and G from, say, whatever. Say this is 2 and a 7. What would you do? You just do the integral from 2 to 7, and you go F minus G. That's pretty easy, right? Pretty simple idea. There's a similar analog that exists with this stuff. So let's do 14 together. I know you guys are dying to do stuff. You're like, I can't wait to do 14.
14 specifically.
Look at the region. Look at Mr. Region. 2 root x.
Didn't even name this one.
Name what?
Didn't name the region.
I know, sad. What's the x value where those cross?
Whoa.
4. Very good. Plug in 4, you get 4. Plug in 4, you get 4. Okay, I guess they cross at 4, 4.
Wasn't that nice?
Now the y value, sure. We know this one we're only going with respect to x. You certainly could revolve this around the y-axis. That's kind of the last thing I'll cover in a day. In a couple days, I'll cover that because I want tomorrow to be work day. Probably Wednesday too. Let's revolve. Revolution. Freedom. As Mel Gibson said. Braveheart. Remember that? Aaron?
Yes.
You see that movie? You
You've
haven't?
never seen that?
Yeah.
Good movie.
I think Aaron was like.
I've never even.
My favorite modern composer wrote
I've
that
heard of
soundtrack, and it was so good.
Oh, I see.
James
I don't think
Warner.
I've seen it.
Yeah, that's right up your alley.
Okay. So here's the idea.
I mean, I've definitely seen like.
If I wanted to carve, first of all, what kind of shape is this? Can you imagine? Can you visualize this shape?
Like a tulip?
Yeah.
It's a really bad bowl.
Is it like a tulip?
Because what's the interior of the bowl? It's a cone. It's all the cereal. You try to stick your spoon in there, unless your spoon has like a ice pick attachment or something. You're never going to get the little bits at the.
So it's
Right.
like a champagne glass instead.
Do we see this? If I tip it side, if I revolve it to create it, tip it side, it's
No,
got like
martini glass.
also has a razor sharp edge. So
What's the cereal?
Oh.
you see what I'm talking about here?
So martini glass.
No, wait, why do you have chance to get off?
Oh.
It is, yeah.
Exactly
Yeah,
what
like
that
With
is.
some extra glass here, yeah, it could be martini glass, yeah. Do you see?
It's like they trick you with how much is in it. You think there's a lot and there's really not.
There you go.
Thanks, Alyssa.
Every type of cereal I've had.
It's a great optics demo about that. You take like a mug that is actually really thick, and this is where the Sody Pop lives. But from
Lives.
Mr. Sody Pop's drinker's perspective, the light goes. So from his perspective, it looks like the Sody Pop fills up the whole. He looks like from his perspective, it looks like the Sody Pop's all the way out, but not. He doesn't see until he looks on the bird's eye view of the glass that there's not that much Sody Pops in there. Sad.
Well.
How does he get his energies? Refraction. You guys probably learned about that in like middle school science.
That was a while ago.
Light bends when it hits the glass.
Yeah, I think I learned
Okay.
in school science with
Anyway.
the solar system.
Revolve. So now the idea is, if you were going to make this, couldn't you just cut out the outer solid and then remove the cone, basically?
Yeah.
Okay. So the idea then is this volume would be, you could go, well, integral from 0 to 4 of pi r squared. Do you understand that?
Mm-hmm.
So this describes if I just revolved that 2 root x curve around, I have this big solid shape. And then we're going to remove the inner shape, so same bounds. Forgot the pi, sorry. Do you feel okay about that?
Mm-hmm.
Where did you get the pie?
The circle, previous problem,
Oh, pi r squared, okay.
pi r squared. But wait,
There's more.
quick thing. Could I write this as, just like before, if you remember last time we showed, I could do this area minus that area, or I could lump it all into one integral. Well, We can do the same thing here, but be really careful. Notice they both have a pi, so let's factor out the pi. And we could have written it as this. So this is actually kind of like a famous formula. If you think about it, it's like pi times, if I call the bigger R R1, the littler R R2, R1 squared minus R2 squared. Which, if you think about it, last remark here, each cross section would be like a washer. I'll cover this, I'll finish this tomorrow. If you think about the area of the washer, you'll see why this makes sense. It'd be pi times big R squared minus little r squared. All right.